In this video, we're going to continue working with the quadratic formula for Algebra 2, and we want to again practice identifying the a, b, and c value for each problem, and we're going to calculate the discriminant as well. In the last video, or the last lesson, we noted that when our discriminant came out to be positive, that there are two real number solutions for our variable. If the discriminant was equal to 0, then there was one real solution for x, our variable, and then if the discriminant came out to be a negative number, then there are two complex or imaginary number solutions for x. We also said that there were no real solutions for that. We started to talk about that if the discriminant d value is not a square number, if it doesn't have a nice square root, then either A, we'll have to complete the problem by hand, which we've yet to talk about in class, or we can rely on the TI Inspire to reduce the result for us. So at the beginning of this lesson, I've got a handful of quadratic equations. They are all equal to 0. So I would like for you to pause the video and use the discriminant to determine how many real number solutions that each question would have if you were to execute this using the quadratic formula. So pause the video now and resume playback in a moment to check your work. So in this series, I noticed that for part A, we had a b value of 4, an a value of 1, and a c value of -1. When we sub those values into the discriminant computation, using the calculator, I see the discriminant came out to be 20. Since that's a positive number, I know that there's going to be two real number solutions to this original equation. In part B, we had a b value of -12, an a value of 4, and a c value of 9. When executed with the calculator, I got a discriminant value of 0, and since discriminant was 0, then there would be one real number solution to this original problem. And then lastly, for part C, our b value was -2, a value was 1/3, and c value was 4. When executed in the calculator, I got an answer of -4/3, or -1.3 repeating. Since that's a negative number, though, I know that there are no real number solutions to this original equation. We didn't have to solve the problem, but we did want to know how many real number solutions that there would be. Let's now see the quadratic formula in action with a real-world problem. We have a rectangular building lot that is 8 feet longer than it is wide. It has an area of 2,900 square feet. Our question is to find the dimensions of the lot. Well, if we know that we're dealing with a rectangular lot, I think we might want to start with this. The area is equal to the length of the lot times the width of the lot. We were also told that the total area of this lot is 2,900 square feet, and the length is 8 more than the width. So if the width is unknown, maybe we can call that x. Then the length would be whatever x plus 8 is. At first glance, this may not be very helpful, but if we think about some of the tools we've learned in the last couple of weeks, we might recognize this x, although it's written in a different position, can be distributed into the equation. So we have 2,900 equals x squared minus 8x. And this is, plus 8x, and this is starting to look like a quadratic equation. The last thing we need to do is move this 2,900 over to the right-hand side, because in order to use the quadratic formula, we want the equation to be equal to 0. So by subtracting 2,900 over to the right-hand side, we're left with 0 equals x squared plus 8x minus 2,900. And with our expression or equation set up this way, I think we can proceed with the most recent methods. We have an a, b, and c value that can be identified. A is 1, b is 8, c is -2,900. The d value, or discriminant, is the opposite of b. Not the opposite of b, my mistake. This is b squared minus 4 times a times c. And off screen I've got a calculator doing this math for me. I see that this discriminant comes out to be 11,664. That's a positive number, so I know there's two real number solutions out there. we would just need to know what the result for this calculation is going to be. That's the opposite of b plus or minus the square root of 11,664, and all of that divided by 2 times a, or 2 times 1. So since there are going to be 2 answers here, I might set myself up to see both of those answers. One solution comes from us using the plus sign in the equation, and one comes from the minus sign in the equation. We are a little bit lucky here in that the number 11,664 does have a square root, so I'm going to see what negative 8 plus the square root of that is. Now the square root is 108. We'll add those together and divide by 2, and then we'll also take negative 8 and subtract 108 and divide that by 2. That's the result that we're looking for. Now this answer comes out to be 50, and this answer is negative 50. Now remember, x was representing the width of the plot, so the width of a real-world plot can't be 50. That's not possible, so we can throw it out. And evidently, it sure looks like that the width of the rectangular building plot is 50 feet. So we know that our width is 50, and if our width is 50, then our length has to be the width plus 8, or in other words, 58 feet in length. So I'll try to color code these results a little bit better. This 50 was our width, and the 58 was our length. By the way, did you notice that 50 times 58 equals 2,900? And more specifically, if we had, let's see, which one do we want here? If I had a positive, if I had a positive 58 but a negative 50, those multiply together to make negative 2,900. And if I had a negative 50 plus 58, that would have equaled 8. Now, what's so special about those facts? Well, that just means that our original problem back here was actually factorable. We could have used our factoring techniques from 2 weeks ago to actually finish this question without using our quadratic formula. Now, I know the quadratic formula is the one that's most commonly used right now, so that's what's on most of our minds. It's perfectly fine to use, but I did want you to see the connection here. In this next example, we're told that the height of an object that's fired straight up in the air is dependent upon the amount of time that it's in the air, as well as the initial velocity, or how fast it was moving at the very beginning of the event. In this particular case, we have an object that's being thrown upward with an initial velocity of 800 feet per second. So we're going to use the number 800 in place of our initial velocity. 800 is our initial velocity. So the equation that we end up needing for this particular example is negative 16t squared plus 800 times t. We can see that down below. If this is the height of an object after some certain amount of time, we can start answering some questions. We can determine when will the bullet fall back to the ground. We can also determine when will the bullet be at a height of 6,400 feet in the air. When will it be 2 miles in the air? And we can also, with a little bit of extra effort, determine how high is the highest point that the bullet reaches. Now this one's a little bit different. We're going to have to rely on a different component rather than the quadratic formula to answer this, but we'll go ahead and work through the solution here as well. I think we'll end up using a graph for this one. All right, so for question A, well, when does the bullet fall back down to the ground? Well, the bullet would fall back on the ground when the height is equal to 0. So if I let h equal 0 in this equation, then I'm going to have 0 equals negative 16t squared plus 800t. Now, I can go ahead and solve this as it is because we have a quadratic equation equal to 0. Our a value is negative 16. Our b value is 800, and our c value is 0. Now, in the interest of time, I'm not going to calculate the discriminant here. This is a real-world problem, so I suspect 2 real answers for this particular example. Let's just go ahead and use our pre-programmed formulas. The QFP at 16, 800, and 0, and then the QFM at negative 16, 800, and 0. If we execute the quadratic formula with a plus sign and a minus sign, we should see the 2 results that we would expect to see from this particular equation. Now, if I run the QFP program, and by the way, in case you forgot, let's see here. We're not going to save this. If you've got the calculator that you had programmed in class, when you choose the Browse option, you should see the quadratic formula program that you saved. So I'm going to call that up again, just to start with a clean slate. And now we'll execute QFP, quadratic formula plus, with our A value of negative 16, our B value of 800, and our C value of 0. And we end up getting 0. That's kind of interesting. We'll figure out what that means in a second. And then QFM, let's go ahead and execute it. QFM, with the same numbers, ends up being 50. So what's going on here? Why does this one say 0 and why does this say 50? Well, remember, this calculation is determining the height in the air that the object is after a certain amount of time. We've just solved that our t value is our independent variable. We just solved t to be 0 and t to be 50 seconds. So evidently this tells me that at 2 points in time, the bullet is at 0 feet in the air, at time 0 and at time 50. Well, that should make sense, because the problem did describe us firing a bullet up in the air from the ground. So at time 0 it was on the ground, it went up into the air, and it came back down. Evidently at time 0 and time 50, that's when the bullet was 0 feet in the air. So it must have come back to the ground at time 50. So even though we didn't look at a graph, we were able to get our answer here. I think we can claim that the bullet returned to the ground, or ground level, after 50 seconds. Let's take a look at part B. Now in part B, the question is, when does it reach a height of 6,400 feet? Well, again, height is the value, 6,400. We can replace h with 6,400. If negative 6,400 is equal to negative 16t squared plus 800t, then by isolating this equation, by moving this 6,400 to the right-hand side, we now have an a value of negative 16, a b value again of 800, but this time we have a c value of negative 6,400. So with a, b, and c identified, we should be able to use our quadratic formula, both plus and minus, in order to compute the time, t, when the bullet is 6,400 feet in the air. So we'll go to the calculator in just a moment with negative 16, positive 800, and negative 6,400 for our values for A, B, and C. And we'll be sure to calculate both of these values, negative 16, 800, and 6,400. Because I don't know about you, but I'm thinking about this graph over here. It might be possible that this thing is, let's say 6,400 is right here. There might actually be 2 times on the way up and on the way down when that bullet might be 6,400 feet in the air. Let's see what the result from the calculator says. So it's still set up the same way as before, so I'll jump up here for QFP, and I'll change 0 at the end to negative 6,400. And I'll also run the QFM value, same way, with negative 6,400. And sure enough, I think my initial suspicion was true. The time at which the bullet's at 6,400 feet occurs at 10 seconds, and it also occurred at 40 seconds. So that happened to be somewhere in between after the bullet was originally fired and before it came back to the ground. So we have a value of 10 and 40. We're going to go ahead and call this 10 for t and 40 for t as well. So at 10 time equals 10 seconds and at time equals 40 seconds, the bullet is 6,400 feet in the air. Now for question C, we have a slightly different approach. The bullet is 2 miles in the air. And what I hope you recognize is that 2 miles is 2 times 5,280 feet. So if we double 5,280, I think that's, what is that, 10,560 or something like that. We'll go ahead and use that new value for our A, B, and C components of this equation. So fortunately for us, not a whole lot changes from line to line. The A value doesn't change, the B value doesn't change, and so far all that's changing is our C value. And I did confirm that to be 10,560. Notice it's positive on the left side, so when I subtract it to show up on the right side, it comes up as a negative 10,560. So here again, I can use the quadratic formula with an A value of negative 16, B value of positive 800, and C value of negative 10,560. And I have a hunch that I may want to try to use the discriminant computation here, but I'm not going to, just so that we can be consistent with the last two examples. Let's take a look here. QFP, QFM, same numbers as before, negative 16,800, only difference being negative 10,560, and negative 16,800, negative 10,560. Let's see what we get. Okay, so if I run QFP, jump up here, it'll be easier, with negative 10,560, and if I run QFM with negative 10,560, we end up getting these weird answers with the letter I in them again. If you remember from last video or from our last conversation, these are imaginary number solutions. I'm just going to make a note here. It's not a real solution, not a real number. And same thing with QFM. This was not a real number. So what's that mean? Why do we say real number versus imaginary number, or real number versus complex number? Well, I think what you should recognize here is that this implies that there is no way to solve this equation using traditional numbers that we're used to working with in an early algebra class. We have no number that would make this equation equal to 0. We have no number that would make this part of the equation equal to 10,560. In other words, the bullet does not reach 10,560 feet in the air. The bullet does not reach, or will not reach, 2 miles in height. That's 10,560 feet, so I'll go ahead and report that. The bullet will not reach 2 miles, which is 10,560 feet in height in the air. So we were able to interpret that, we were able to observe that simply because the result of the quadratic formula produced an imaginary result. And before I even computed that, I made a comment saying that it might be worthwhile to calculate the discriminant. We could have saved a little bit of effort by calculating the discriminant ahead of time and noting, we would have noted that the discriminant came out to be a negative number, which implies that there's no solution. Now back to question D. I'm going to put a star next to this because we're going to be using a graph to solve it. If we graph the original equation, not A, B, or C, but the original equation with h equals this expression. In fact, I might have to change it just a little bit for our calculator. I'm going to graph the equation, not h equals, but y equals negative 16x squared plus 800x. We should be able to calculate, or to graph this and see all of the same features that we just described a minute ago with the equations. We can see them in the graph itself. So I'm going to just be prepared to draw a quick sketch here. Let's go take a look. So I just went out to Desmos here for ease of use, and let's go ahead and graph this equation. I've got, and I'll turn this on bold for us. Okay, so I have y equals negative 16x squared plus 800x. We changed some of the letters around to make it a little bit easier to graph. And so now all I need to do is adjust the zoom. Since my computer is a touch screen, I can zoom in one direction or another. So I'm just zooming out on the y-axis temporarily, and then I can adjust the x-axis as needed. Now this graph appears to represent the trajectory of the bullet. It goes up a certain height and it comes down within the 50 seconds. Now we can see those two answers here by clicking the x-axis. The bullet was at a height of 0 when time was 0, when x was 0 or t was 0. The bullet was also at a height of 0 when time was equal to 50. If I had graphed the equation y equals 6,000, oops, not 600, but 6,000, we can see the two times when the bullet was 6,000 feet in the air. I don't think that looks right. Was it 6,000? 6,400, sorry. We were 6,400 feet in the air. Let's fix that. Change that to 6,400. There we go. Now we can see the times when the bullet was 6,400 feet in the air. We just drew this horizontal equation with a target height, or y in this case, of 6,400. Y equals 6,400, and that gave us a position to match. Now for our third example, we had y equals 2 times 5,280, and you can see here that that height is 10,560, and we can also see that this red graph never quite reaches that green line height. It never quite reached that target. So it came up just a little bit short. It reached a height just a little bit less than that. It appears to be 10,000, but it didn't quite reach the height of 2 miles, 10,560. So since we're here on the graph, we can click on the screen with Desmos, and this screen tells us the answer to question D. Question D is asking what is the highest point that the bullet reaches, and by using this graph we can see that it occurred right here at this coordinate, which was 25, 10,000. And what does that coordinate tell us? Well, the coordinate tells us that the max height, H-E-I-G-H-T, is 10,000 feet. The y value represents our max height. And when did that occur? Well, that occurred after 25 seconds. And what I hope you realize is that our bullet was on the ground at 0 and it was back on the ground at 50. This maximum height, 25, occurred exactly halfway in between. And that's a behavior of these parabolic functions, or these quadratic functions in these parabolic graphs. We'll see that from time to time. Now this video is starting to get a little bit long, and I'm looking at the next two examples here. They're essentially the same as what we had started with, so I don't think we'll cover those in this video today. And I have one more application of a quadratic, but again, here in the interest of time, I'll cut this short. So I'm going to pause the video for a second, and then I'm going to show you the answer solution to this. Basically, we're taking a flat piece of cardboard, we're cutting it into a box that has a square base to it, and we'd like to be able to calculate the volume associated with that square-based box. So I'll flip over on the screen here. You can take a look at it and try to make some sense of it, and if we have some time, we'll talk about it in class this week. So here we are. We essentially have found the volume of the box, substituted in some dimensions that were given to us in the problem. This simplified down into a quadratic formula expression, quadratic formula example, and x ended up being 13 or 3. Where x represented the amount of the width of the cardboard sheet before we cut this 4-inch corner out of it to fold up the box. As it turns out, with an x value of 3, that's too short for us to actually generate a box, so we had to commit to an x value of 13. So if the length of the box was 13 and the width was 13, the height ended up being 4, and we have a volumetric solution that's equal to our target here of 100 cubic inches. So I know that's a lot, and I didn't even explain it very well in this video, but take a look at it, read through it, see if it makes some sense to you, and we'll talk more about it in class when we see each other next. Thanks for watching.